on. So what I'd like to do is actually go through assignment 7 now. And that, I think, is going to be a great prep for those people that are planning to take the exam, because it covers basically the same material. The exam covers correlation and linear regression. Does not cover multiple regression, does not cover logistic regression, right? So I'm going to go ahead and open that up. Okay, and if you have questions on this, type it into the chat box. And we're a relatively small group tonight, so if you want, if you alert me, I can, right now I muted everybody's microphone so we don't have a lot of background noise. But if you want, if you have a question, just type it in the chat box to ask me to turn on your microphone so you can actually speak your question rather than type it in. If you prefer, though, you can just type it into the chat box instead. All right, so, and like I said, a lot of this has to do with responding to people's concerns about some of the problems on assignment 7 that also relate to stuff that's going to be on the exam. So I really think that that's probably a good way for us to deal with this. Okay, so I'm going to start the exam. So this is basically the same way you see the, not the exam rather, assignment 7. This is basically the same way that you see number 7. So in here, the first question is, students are randomly, oh, that's great spelling. They're randomly selected for a study attempting to investigate whether or not there's an association between the number of missed classes and test scores. The results of this study are as follows, also available in assignment 8, correlation. I changed the number on there to assignment 7, you know, so that it makes a little bit more sense. I'll change it here also when we're done. But here you have the test, you have the number of absences, and the idea here is that we're looking for an association between two numerical variables. One numerical variable is the number of classes that a student missed. The other numerical variable is the test score that they got at the end of the semester, for instance, say on a final or something like that. That association, we give that association between two numerical variables, we give that a special name. We call it correlation. Okay, so that's a term that we use for specifically that kind of association between two numerical variables. Okay, and obviously you would say to yourself, well, it makes sense that there's an association. If you miss a lot of classes, maybe you won't do as well on the test when it comes up, right? So we can see that this is a reasonable expectation that there might be some kind of association between these two numbers. Now, the way I just stated it, it implies that, oh, if you miss classes, you must do terrible on the test. Well, we're realistically, you know, I know some students that, for instance, may have taken statistics very recently at some other institution, and they know it very well, and they can manage to miss a lot of classes and still do very well, right, on the exam. So, I mean, hardly makes any sense to us now with these online courses, right? Because you can basically do it anytime you want. There really is no way to miss a class except not ever, you know, look at it. So at any rate, so that kind of implied, the way I stated it kind of implied that there's some causal relationship between those two values, right? And in fact, you know, in this case, there likely is, right? Not absolute, but there likely is, right? But the important thing is correlation doesn't require causation. In other words, maybe there's an association between these two, but it's not, it's just, it's spurious. It's due to some other, because they're both related to some other thing. And it's not actually the absences that are causing the test scores to get better or worse, right? So when we're talking about correlation, we don't assume causality. We assume, okay, let's see if there's an association between these two. And it might be real, it might be not. For instance, maybe I would want to look to see if there's an association between a person's age and their test score, right? Well, I don't think a person's age is likely to affect their test score in this course, right? However, a person's age may suggest they have more time to work on this, they're more mature. So other things that are kind of buried in these variables may cause that to maybe a real association, but not directly caused by one or the other variable, just an association that we can demonstrate that as one goes up, the other goes up, or as one goes up, the other goes down, but not necessarily that causing it specifically. The example we used in class was The number of firemen that show up to a fire versus the number of dollars worth of damage that's done at the fire. Well, obviously, you get more firemen a fire, it's probably a bigger fire, so the amount of damage is greater. That doesn't mean that's a real association. And if we had the data for it, we might be able to prove it's a true correlation and statistically significant, right? But it's not firemen causing the damage, it's fire causing the damage. The fact that there's a lot of damage means it's probably a big fire, so naturally a lot of firemen, more firemen have to respond to it, right? So correlation doesn't mean causality. So in this first question, we're asked, calculate using SPSS or other tool. I don't think really it's no on a practical basis, not going to be another tool, right? For us anyway. If you know R, you could use R. Excel is not probably a great tool for this. Calculate using SPSS or other tool the value of Pearson's correlation, R. Okay, one of the questions on Blackboard was, what is this R? Where did that come from? What does that mean? Well, R is the Pearson's correlation coefficient. That's the number that tells you how strong an association you have between two variables. And interestingly enough, just like all the other variables that we work with, when we talk about the association for the entire population, the strength of association for the entire population, we use the Greek letter rho. When we talk about the association between two values in a sample, two numerical values in a sample, we use the English letter R, right? But they're associated, rho and R, basically measuring the same thing. One indicates it's a population measurement, the other indicates it's a sample measurement. Okay, and we're asking you to include the correct sign, positive or negative. We're going to get to that again and discuss what that actually means. And in fact, I think before we go any further, I think now's a good time for me to just lay this out graphically. So I'm actually, first thing I'm going to do, okay, let me do this first. Okay, so let's say that I have an association like this. Okay, let's say that, for instance, in this situation, one absence was 95, 6 absences was 56, and so on and so forth. So if I drew a graph, this is called a scatter plot. And in the x-axis here, we put the number of absences. And in the y-axis, we put the test score. Okay, so let's say number of absences 1, 2, 3, 4, 5, 6. And let's say that one of the students missed 2 classes, and their test score was, it's 100, and maybe this is 50, maybe this is 25, maybe it's going to be hard for me to go below that because most of them are between 55 and 100. So I missed 2 absences, and he got a score. A person missed 2 absences and got a score of 90 on the test. I've just laid these out, so these are coordinates on a graph. The x value is 2, the y value is 90. That's one subject. So the 2 and 90 would represent a dot up here. Let's say the next student missed 5 classes, and he got a score of 70 on the test. So here he is out here, 5, and he got a score of 70. So maybe the coordinates for that would be 5, 70. 5 across and 70 on the y scale. Maybe another student got a score, missed 3 classes, and he got a score of 82, right? So for 3 absences, this person got a score of 82, 3 and 82, so he might be over there. So you might have noticed that these are starting to line up so that even though I can't draw a straight line that goes through all of those, but I can draw a straight line that approximates where the relationship between the x-axis and the y-axis, between the absences and the test scores. I'm not going to go into a lot of detail about how this line is determined, but it's basically looking at the variability between the line and between the x values and the y values, and it's balancing these so that the squares of these differences basically are balanced, they're equal on the top of the line and on the bottom of the line. So the other dots might wind up like this, right? But in general, you can see that there is an association that looks like that as you go up in absences, what happens to your test score? Your test score goes down. Okay, so let's look at what kind of graphs then we might get here. Okay, one graph may look like something like this. And all of those lines fall perfectly on a straight line. Another graph may look like this. All of those values, again, landing on a perfectly straight line. Or you might get something like this, right? Or maybe something not quite so nice, something like that. Or maybe you'll get something like that, right? So what do we have here? This is a perfect, this one over here is a perfect positive correlation. Positive correlation. Okay, in a perfect positive correlation, these all are perfectly on this line that will join all of them as perfectly predictable. Whatever change you get next will perfectly predict what the value y is. They all land on a straight line. Okay, that has a Pearson's correlation coefficient of r is equal to 1. When you have a perfect correlation, it's equal to the number 1. Okay, so this one is also equal to the number 1. It's also a perfect correlation. But as the x value goes up, the y value goes down. So this perfect correlation is equal to -1. So the r values take values from -1 to +1. This one down here is basically just a cloud of dots, right? So really, the best you could do is maybe draw the line straight across, which what does that tell you? That tells you no matter what the x value is, the y value is not really predictable. It's the same, the line is the same. It doesn't make any change on it, right? So that is called an R value of 0, no association whatsoever, right? So in between those, you have sometimes a strong association, but not perfect. So this might be an R value of plus 0.8. And this one, I can see an association there, but the points are a little bit further off the line than this one. This might be an R value of plus 0.3, right? So that's that's how we visually use the scatter plot to get a look at this and get a rough idea of whether or not it's worth pursuing, whether or not there's an association between these two values. Okay, so that's what we have there. So now I'm going to actually do this with the data that we have. Okay, so actually you could literally just copy and paste this into SPSS, but we've given you the values in the data set. I just changed the name to assignment 7 and assignment 7 here just to, so it goes with the right assignment number. I'm going to open up SPSS and open up that data set. Okay, you guys can give me feedback. Let me know if this is working out okay for you. Or if there's somewhere where I go off track and I lose you, let me know also. So be prepared when you take the final exam. Be prepared to look at a scatter plot and make a judgment in your head. Is that a 1? Is that close to 1? Is that lower than 1? Way lower than 1? Is closer to 0 than 1? And so on and so forth. Okay, and there it is. Okay, so here is our data in SPSS. And you'll notice that they're both, they should, now you may have to go in here and change this to scalar because SPSS sees those absences as integers and it may be thinking, oh, maybe that's like ethnicities or something like that. It's guessing that maybe that's a nominal variable, but it really is a scalar variable because it's a number of absences. Okay, so I'm going to look for this association. The first way I'm going to look for this is I'm going to look for it graphically. So I'm going to go up here to Graph, Legacy Dialogues, Scatter Dot. And I'm going to tell it I want a simple scatter dot. Okay, and with correlation, it doesn't matter which one I put into the x-axis. In the y-axis, I'll get the same value as far as the correlation coefficient is concerned, that R value is concerned. I'll get the same value. So it doesn't matter. But you know, since I already am thinking that maybe the absences is the predictor variable, also called the independent variable, since I'm thinking that way anyway, maybe I'll put that into the x-axis. Okay, and I'll put the test score into the y-axis, the predicted or the dependent variable. I'm going to click OK, and we're going to get a graph. Okay, and it does look like this data trends downward. As the absences increase, it does look like there's an association between test score and absences. It looks like it's a negative correlation. Okay, now just a dirty little secret. If I double click on this, it opens the editing window for the chart. I can actually create that line here. I go click on there for a fit line, and just open it and close it. It automatically creates it. It's created that line that balances. Oops. It's created that line that balances the values that are above and below this line. Okay, so that gives us an idea. That looks like what the association is like. In other words, how quickly, as we go up in absences, how quickly the test scores fall. Okay, now that's interesting because now we say to ourselves, it looks like I have a pretty strong correlation over here. And looking at this graph, think to yourself, what do you think the R value is going to be on here? Well, first of all, what sign is it going to be? I'll give you a second to think about that. And what do you think the number is going to be? So I'm looking at this and I'm thinking, it's a negative correlation. So the R value is going to be negative. It's not perfect because they're not all lined up on that line, but it's really, they're pretty close to that line. Not scattered around a whole lot. So I'm thinking that that's a negative correlation of 0.7, 0.8, right? So negative 0.7 or 0.8 is what I'm kind of thinking in my head. I haven't done any real calculations, but just looking at it. So I'm going to close this, and I'm going to go to analyze, and I'm going to go down to correlate, and I'm going to go over to bivariate, two variables. And that's what we're doing here. All these problems that we're working on, always going to be two numerical variables that we're working with, at least in linear, in correlation and linear regression. Okay, so here it's asking me, well, which variables do you want to test for the Pearson's correlation coefficient? Which one do you want to test for an association? Well, notice it doesn't care which one I put in first or second. All it cares is that I have at least two of them in there before it lets me go to OK. Okay, and that's because, again, correlation, you're not making a judgment about which one causes the other. So it doesn't care which is the X and which is the Y. So I'm going to click OK. And I'm going to wind up with a result. This correlation table tells me the Pearson's correlation coefficient, which is, what do we call that again? That's either rho for the population or R, right? The R value is equal to negative 0.91. So that's a very strong negative correlation. In other words, it looks like there's really a strong association between these two values. That attendance really affects the test scores, right? And it's a negative correlation. As attendance goes down, as attendance absences go up, the test scores go down, right? Hence that negative sign in front of there. So that's our negative correlation. The next number that's important to us here is this significance, a special kind of ANOVA test that's done to see if this correlation coefficient is truly statistically significant, or if it just happens to be due to chance, that we had very few people in the sample, and even though it made it look like there was an association, it could be just coincidental, right? Well, what are we looking for there? We're looking for a significance or a p-value, which is less than alpha, our acceptable level of chance, right? Acceptable level of being wrong if we reject a null hypothesis. And we want that always to be less than 0.05, not always, but most often less than 0.05 before we reject the null hypothesis. This is a great time to talk about null and alternative hypothesis here. So Let me open up another sheet. Okay. So I can make this a little bit smaller without it crashing on me. Okay, so talk about the null and alternative hypothesis. So our null hypothesis here and our alternative hypothesis here, if I want to put it into words, and this is for the correlation coefficient, correlation. If I were to put it into words, the way I would say this is, my null hypothesis is that there is no association. Remember, it's null, so it's basically no association between absences and test scores. And my alternative association is that if I can reject that, I'm going to say there is an association. And because we're statisticians, we could substitute the word correlation for association. Okay, there is no correlation between those, or there is a correlation. Use either one of those words. But even a better way to phrase our null hypothesis. Null hypothesis. Okay, what did we say? I'm going to start with our null hypothesis. When there was no association between one variable and the other variable, and the points were just a cloud. They didn't go up or down. The line couldn't draw a line that went up or down through it and stuff like that. What did I say the R value was? I said the R value was equal to 0. So our null hypothesis is that the R value is equal to 0, meaning no association. And our alternative hypothesis is the R value is not equal to 0. It's equal to some other number, even if it's 0.1, and it's like just a very slight association. It's different than 0. And what do we have to accomplish to be able to reject the null hypothesis and say that there is an association? In other words, R is not equal to 0. We have to make sure that our significance is less than 0.05. Okay, we want to make sure that our p-value is less than alpha, less than 0.05. Okay, so that's you could phrase these either way. Okay, so I'm gonna get this out of the way. So that's our null hypothesis. So in this case, I'm gonna ask you a question. Can I reject the null hypothesis here? I'm gonna wait for somebody to type it in. Yes, we can reject it because the significance or the p-value is less than 0.05. Had this been 0.21 instead of 0.001, had this been 0.21, even though it looked like we had a very good association, we couldn't say with less than 5% chance of being wrong that it's not due to chance. So we wouldn't have been able to reject the null hypothesis if the significance was, or p-value was bigger than 0.05. And usually that's the result of like maybe too small a sample or something like that. Okay, so that's correlation. I mean, we could talk a little bit more about that, but that's really basically what we're looking for when we're dealing with correlation. So now the next step I can take is I want to better define what this association is all about. So I'm looking at this and I say to myself, it's nice for me to show that there's an association between absences and test scores. But I want to quantify this association. I want to be able to describe how absences affect test scores. And I feel strongly enough that there is an association, obvious association between these two, and that the way that the association works is that absences lead to lower test scores, not that lower test scores lead to more absences, right? In other words, the association goes this way, not the other way. So that if I'm looking at that this way, then what I'm basically doing is I'm assigning the absences the title of predictor or independent variable. If I'm saying that about test scores, I'm assigning the definition predicted value or dependent variable to the test score. Independent variable, dependent variable. predictor variable, predicted variable. Okay, that's the way I'm looking at this. So now that gives me impetus to go to the next step and try to evaluate how strong this relationship is. And for that, I'm going to use regression. Analyze, regression, linear. Okay, so now look what happened here. Look at the big difference that we got here. We got a situation where now I don't have one big fat box to move the two variables into, right? I have two boxes, the independent variable and the dependent variable. Notice you can have a lot of independent variables, get a big box here. If you go back over the videos that we had, that's because you can put several variables in here to use them to predict the value of the dependent variable. That's called multiple regression. We're not worried about this for this assignment and for this particular test, right? Because we're going to deal with just simple linear regression, which is only going to look at single variables. So which one goes into, you tell me which one goes into the independent variable box? Get those fingers typing for me, please. Which one of these two variables is the independent variable? Absences, right, great, perfect. Okay, so that's the independent variable. So that makes the other variable, the test score, the dependent variable. Okay, so now you have a lot of options for statistics and stuff like that. But for the most part, for our purposes right now, I basically have what I need. There's other things we can go back and look at as well. So I'm going to click OK. Okay, so we have more information than we had before. In this case, we have just a report on which variables that we were working with, and we have a result of the correlation, a repeat of the information that we got from the correlation coefficient. And what do we have? We have our R value. See here, they actually call it R, but before it's a correlation coefficient or Pearson's correlation coefficient. Right here, they just refer to it as R, but you can see now that it's the same number, right? And what is it? It's a negative. It's a negative number. Is it negative? Where? Let's see, 0.9. A predictive variable. Oh, they don't show the sign here. Okay, it shows R. It doesn't bother to show the sign. When we did correlation, it did show the sign on there, and we know because of the association that is really negative 0.910. Right? As absences go up, the value of the test score goes down. Okay, so and we also see the significance. This is a more complete test of the significance for this correlation. Comes up to 0.001, the same value we had before, and you'll see that okay, we got those two values are the same as the previous chart. We have another value here called R squared, and literally, if you just take 0.91 times 0.91, you get 0.829. It literally is just the R value squared. That's an important value. I'm going to skip that for now and come back to it because that variable is going to be important to us, okay, for a lot of reasons. Okay, next thing I'm going to do is I'm going to go down here to the coefficients table. And the coefficients table gives me two lines. One is called constant, and the other one is called absences. It has the title of the independent variable that we're using. If we're multiple regression, have several variables down here. But again, simple linear regression, we have one variable down here, the absences. And we have numbers, we have coefficients underneath here that are called B, right? That are under this column called B. Okay, so I'm going to go and I'm going to pull up a sheet of paper again and discuss what those values under the coefficients, the unstandardized coefficients, that B value, what that means. Okay, so now remember that when we're talking about linear regression, we're talking about basically something that describes a straight line. So in this case, it was absences, okay, which is also the x-axis, and it was test score. Whoops. And that was the y value. Okay, so what we saw was when there were very few missed classes, we were up here, we were over here, over here, over here, over here, over here. And the line that we drew, the best fit line, looks something like that. Okay, so now, and it was a negative correlation. So now when I look at that, I say to myself, oh, okay, So now that's great. I have this line that describes how this association works, how in general how in general the number of absences affect the test score. Okay, so I know that if I have a straight line, I know from algebra that I can write a formula that describes that straight line. So for instance, any straight line can be defined as y is equal to mx plus b. Okay, that goes back to our algebra days. That's generally the way a math major would describe this relationship. And what does this line tell us? That tells us that the value of y, right, in other words, that how high up the dot is determined by this m, which is the slope, times x, the slope of the line, times x, plus the y-intercept. That b represents the y-intercept. So that is the slope of the line, and this is the y-intercept. Okay, so let's talk about those values. Well, first of all, if I look at this, and this formula is supposed to represent all the points on this straight line, well, where does that b come from? And why is it called the y-intercept? Between r squared, I don't want to get into that right now. Just worry about using the r squared. Okay, when we're past the test, I'll post something and I'll discuss the adjusted r square value. Okay, I don't want to confuse people on that right now. Okay, I'm concerned right now that we all understand why we're using that value and how we interpret that value. Y-intercept crosses the y-axis, exactly. And if you look at this, where is 0 for x? 0 is the point where the line crosses the y-axis. The value of x is 0, right? It's the axis, right? So if we put in 0 for x, that drops out, and all we have is y is equal to b. So that's why that value is b. That's why it's called the y-intercept. Now the slope is the difference in the change in the y over the change in y over the change in x, right? So the slope is equal to change in y over the change in x. So in other words, the amount that you change, the top part of this is how much y changes for a change in x. So if x changes, if the slope is equal to 3, right? If slope is equal to 3, well that means that if x increases by +1, okay, then y must increase by 3. And if x increases by 2, y increases by 6, right? In other words, the slope tells us that relationship. In this case, it would be a negative relationship, but this is just in general what the slope really means. So what does that mean? That means if we know what the y-intercept is, and we know the slope of the line, it automatically defines this line. If I were to take the same line, same y equals mx plus b with a different b, well, what that would be is, okay, let's say that that's b. Well, the slope of the line, if it's the same, is going to be parallel to that line. So now we know we define that line. So this formula can define a single line. Everything you need to know about the line is in that formula. In statistics, you usually see people refer to it as something like this. Y is equal to beta 0 plus beta 1 x. And in this case, this is the y-intercept. And this is the one that's in front multiplying the x is the slope, just like the mathematical version, the math version, the algebra version of this thing. Anything that's multiplying the independent variable is a slope. Right? Anything that's standing by itself is an intercept in this format. Okay, so so now what I want to do is I want to actually define the line that describes the relationship between absences and test scores. Okay, so here's my output. Move this over a little bit so I got a little bit of room to work. And make this a little bit small. Okay, so I'm going to go over here And now I am going to write this formula. Y is equal, oops, oh my goodness. What did I do? Oh, there we go. Y is equal to, I'll tell you what, Y is equal to beta 0 plus beta 1 x. Okay, so let's think about this. So Y is equal to, well, if I go to this table of coefficients, the beta 0, the y-intercept, is this value that's called constant, 95.963. Now, I always tell you, a lot of people in my classes, do as I say, not as I do. So I used to tell people, don't round until the very end. But I'm going to round here just to make things a little bit more convenient for us. Okay, so the reason for that is that if you multiply something by something else, now if you round a value and it's not the very end of the calculation, if you then square it, find the square root of it, multiply by something, it increases the error at each time you do an operation on it when you rounded it early. So, but I'm going to do this. I'm going to do this because number one, I can. Number two, I need to do this to like just keep things reasonably efficient here. So that's the y-intercept. Plus, now I need to know the value for the slope. Well, absences, negative 5.899, right? So that instead of being a positive plus beta 1x, that's negative 5.9, I'm going to call it. I'm going to round again. Okay, I encourage you, like maybe in this case, you might have taken an extra decimal place that I didn't take. Okay, so y is equal to 96 minus 5.9 times x. Oh, so now we have a formula that describes the line that represents the table that we had before. We have a line that represents this formula. The dirty little secret, remember I double-clicked on this thing and told it to give me the fit line? Look, it already gave me that formula over there, didn't it? Right, so it took the mystery away. I didn't point that out then, but now you can see it's already there. And in fact, we just confirmed it by doing the actual analysis. That's how I would determine what the value for that line is. So now what good does that do me? Well, what it does for you is it tells you a couple of things. Number one, it gives you some measure of predictability. So for instance, if I told you that a student missed 3 classes, what would you predict using this formula that his test score would be? Well, what you would do is you would say, well, y is really the test score is equal to 96 minus 5.9 times x is the independent variable, which is absences. Okay, this formula would predict, well, if he missed 3 classes, I would expect his test scores to be equal to 96 minus 5.9 times 3 absences, right? So we're using this to predict an outcome. This is pretty, like silly exercise here, but try to imagine if we had some measure, some physical measure that we could take of a patient that would be very simple to take, but now we could prove that there's an association between that measurement and some result of an expensive invasive test. Well, now if we could show that there's an association, and we could do a calculation that says, well, if his BMI is this, it predicts that his insulin sensitivity is likely to be this level, right? Or something of that nature. Or if his fasting blood sugar level is this, his insulin is more exhaustive test, including insulin sensitivity, would be this. We can use, if this formula is really predictive, then we could use that to our advantage. That's one thing that you can use it for. The second thing is that, and I'll get to that in a second. First, I want to solve this. So we're predicting that his value for this score is, let's see, 618 minus 18 would be, minus 18 is 8, 878. We're predicting that his score would be 78. I think I got that right. Oh, no, I'm sorry. That would be if it was 16. If we're 18. Yeah, 18, and it's actually, it will be 79.3. 18 point, yeah, 79.3 or 0.7. 79 point, am I right about that? It'll be back in 27, but no, 79.3. Okay, I think it's 79.3 or 78.3. One of the other. You know, I should do the calculation, right? Why not I just do the calculation? It'd be 96 minus not 618, 17.7. Okay, which is 78.3. Thank you very much. Save me the trouble of actually using my mind. 78.3. That's what we predict that his test score will be. Okay, so let's say this guy that took the test, that missed 3 classes, and we predict that this guy's going to get a 78.3. He goes and he takes the test. And the result of it is a resulting real life test score, not estimated test score. The result of his real life test score is 76, right? Well, okay, pretty close. Our prediction was pretty close, so we're patting ourselves on the back. But you know, there's a difference here, right? That difference has a special name in statistics. Difference between what we predict using the regression line, predict that his score is going to be, and what it really turns out to be is the difference between these two, or 2.3. That number is, you could define it 2 ways. You could call it the error, right? And we can even put it up into this formula. There's always going to be always a potential for a little bit of an error. If this were really a full, complete formula, we'd also include that little extra bit for what the error might possibly be, right? We don't need to usually describe it here, but just keep in mind that that could be in there, right? But instead of calling it the error, we call it the residual. That's a statistician's name for the difference between these 2 values, or in effect, the error in the predicting formula, in the formula that you're using to predict it. That's called a residual. Okay, let's take another look at a dirty little secret in SPSS. In SPSS, when I go to analyze and I go to regression and linear, it's still set up unless you quit SPSS and restart it up. It keeps the variables in here. If I go into this button save, I'm going to click on save. And if I go in here, I can ask it to give us the unstandardized predicted values and the unstandardized residuals. And I'm going to click continue and click OK. Okay, so, and our output window is going to come up. And our output window is going to give us some extra confusing statistics down here, along with all the other windows that we had before. But lo and behold, when I go back to my data values, look at this. I have 2 new columns that weren't there before. I have the predicted values and I have the residuals. So in other words, this person, subject number 1, he had 1 absence. He got a test score of 95. Our formula predicts that with 1 absence, you get a test score of 90. And the difference between 95 and 90 is the residual, or the error. So it actually will give you what the line would predict for each one of these values and what the residual value is. Now, one of the things we're interested in is that these residual values, they're basically chance, right? That whether or not a person is higher or lower, so you would expect them to be distributed normally. So in real life statistics, you might take these values and you might actually test them to see if they're normally distributed, that the errors are typically, more often than not, the errors are a small difference, and then it's rare for them to be much different on either side, positive or negative, +4, -5, and so on and so forth. And if they're not normally distributed, you start to worry about whether there's some other stuff at work here. And in fact, you can actually, if you go to analyze regression, you don't have to worry about this for the exam. Okay, if you go into this and you look at save, there's also, you could actually have it give you standardized versions of the predicted values and standardized version of the residuals. In other words, that's actually the Z value of each one of those residuals or differences. So you could look to see if it's really, it makes it easier to see if it's normally distributed. You don't have to worry about that. This part is not on the exam, not directly on, not in an intense form on the exam. This idea of residuals though is on the exam, and calculating a residual is on the exam, right? So we have that gives so that I think gives you a pretty good introduction into this. So let's go through the homework. Let's actually go through the homework, see what we have to do. Okay, so how would you describe the strength of this association? What do you think? I think that's a strong association, right? I wouldn't say weak, wouldn't say none of the association, certainly none of the above. So that's a strong association. It has to be a negative, but it's a strong association. As the number of absences increases, the test score suffers. This would be described as a positive correlation. That's not true, right? As the absences increase, the test scores go down. That's a negative correlation, right? So that would be false. You perform a simple linear regression analysis with the number of absences as the independent predictive variable and the test scores as the dependent result, which you just did. How much of the variability in the test scores do you estimate can be attributed to the absences, the predictor variable? Express as a two-digit number. For example, 34.9 or 0.3, enter like 35. In other words, if that's clear as mud, right? Express as a two-digit express. Okay, so I need to go back and review something briefly that I said that I was going to go back to, but that question reminded me that I didn't go back to it. You guys remember a little while ago that somebody even prompted me about the unstandardized, about the adjusted R square? Let's see where the R square is. Okay, here we go, adjusted R square, and here's R square. So R square, what does R square tell us? Okay, actually it's just the correlation coefficient squared multiplied by itself. That R square, that actually has function in understanding this relationship. That number 0.829, that tells us that 82.9, say 83%, 83% of the variability in the test score is due to the predictor variable, the number of absences. Now, between me and you, that doesn't make much sense, right? I mean, we wouldn't think that 82% of your grade is just showing up, right? There's a lot of other things, other factors, but it does show you that 83% may be due to that test score in this instance, but that means that there's 17% of the variability in the predicted variable, the independent variable, is due to other factors. So it's not unusual for that number to be quite a bit smaller, right? So the R square tells you, informs you about what percentage of the variability, the change in the test score, is due to the predictor variable that you're using, the number of absences. The other variables that you could test and use the predictor variable might be how many hours a week that the students study. And that might be equally strong an association, or even a stronger association, right? So that would have its own R value and R square value and so on if it impacted this. This is artificial data, so things get funny with artificial data. So for instance, so in this particular case, how much of the variability in the test score do you estimate to be attributed to the absences, the predictor variable? Well, that's what R square is for. So that would be 83% of the variability in the one variable is in the dependent variable is predicted by the number of absences. So what this is saying, for instance, if it's 83% or 0.89, right, and just enter the first two digits. In other words, 89%, 8.80, just not 0.89, but just 89. That was just to make it easy to enter the value. I'm not sure I made it easier or harder, right? But that's what that question's about. You propose a formula representing the association between these two variables. The test score is equal to slope times the absences plus the y-intercept. In other words, beta 0 plus beta 1 times beta 1x. Excuse me. This is beta this is actually in the form mx plus b, or beta 1 times x plus the y-intercept. So what's the slope? This based on your analysis, what is the value of the slope? Include the sign if it's negative. So what was the value of the slope? The value of the slope was, where is it? There it is up here. The value of the slope was negative 5.89. And okay, so that would be negative 5.89 would be the answer to that question. Again, you propose this formula. What's the value of the y-intercept? And include the sign. And in that case, it's a positive 95.96. Okay, and based on your regression formula, if a student missed 5 questions, what would you predict his test score to be? How would we, yeah, good work, thank you. You guys you're keeping up with me there. Okay, based on your regression formula, if a student missed 5 classes, what would you predict his test score to be using the formula that you created? You guys go ahead and give me the answer to that. Okay, 66.51. Okay, that sounds right to me. That sounds good. 15 points for you. Okay, so that's good, right? So that's exactly what we're looking for. Now, it turns out that that student actually scored a 70 on the exam, not 66.51, right? So what's the residual value for this result? Well, the residual value is the difference between what you predicted his score was going to be and what his score actually was. So what's the residual value? And I think I asked you to put it in with no sign, just a number. 3.49, exactly right. That's what this is all about. Now I want to just do one more example, and I want to do it say with semi-real life data. I'm going to use that North Carolina data. So that's this homework. That's basically all that was on this homework. And the exam is a bit more detailed and has maybe a few more multiple choice questions, but it really covers this same material. So if you can get through this, you should be in pretty good shape for the exam. Let me just find NC birth 800. If I can come up with a copy of this quickly. I have 8,000. I keep doing this. I wind up with 8,000 copies of this silly file on my computer. I'm going to say open data, navigate to my desktop, and find that file. Okay, so I'm going to look for a relatively simple association. I'm going to look for the weight gain. How about weeks of gestation and the birth weight of the child? This is the number of weeks of gestation. It's a numerical variable, and this is the birth weight of the child in ounces. I want to see if there's an association between the two of those numerical variables. They're numerical, so the test I'm going to do is, they're both numerical. The test I'm going to do is correlation and regression. So first thing I'm going to do is I'm going to go up here to Graphs, Legacy Dialogues, go to Scatter Dot, and I am going to, I'm going to have to pause for a second and take care of something. I'm going to just pause, turn this, I'm going to pause the recording.
This conference will now be recorded.
Okay, so we should be back. You can hear me again, right? And you can see my screen. Okay, great. Sorry for that interruption. Okay, so let's take a look at this simple scatter plot. I'm going to click simple scatter plot. Now, just so you know, let me just click into matrix scatter here. Define. What you can do here is that you can actually evaluate, view a lot of variables at the same time. So let's say I was curious to see if completed weeks of gestation, if the let's say it's got to be numerical variables, weight gain during pregnancy, and the weight of the child, okay, and any other numerical variables here, the age of the mother. Whoops, yeah, those are all numerical variables. That one is 2. SPSS thinks it's a categorical variable because they're all integers, but we can change that when we go back and click OK. What this does, when you put it as a matrix, it actually produces a graph. Processing. There you go. It actually produces a graph that looks for an association between all of these. These look kind of like, ink blots because there's just so many values. it's hard to see them individually. So look here, this looks like a strong linear positive correlation. What is that? That's weight of ounces to completed weeks of gestation, a strong association. This looks like a weak association, positive association. Well, what is that? That's the weight gain during pregnancy and the weight of the child. That seems reasonable too. This one looks like it's no association whatsoever. And that's the weight of the child in ounces and the age of the mother in years. That makes sense. Maybe there isn't an association between those two. So you can look at this and try and make up your mind which of these look like positive correlations, negative correlations, which ones look like no correlation, like this one look like no correlation at all. The age of the mother and weight gain during pregnancy, no correlation. It's just like a blob, a horizontal line, right? Yes, one side. Yeah, what they do here, SPSS does this constantly. I'm not sure why, but what they do is they take each individual variable and compare it to the other three. And then they compare, and then they do the same thing in the other direction. So if you look at this, you have the weight of the child and completed weeks of gestation. And then over here, you got completed weeks of gestation and the age and the weight of the child. It's the same analysis. So it really just does the same ones twice. It reverses them and does them again. So you may have noticed it also does that when you do your post hoc test. It does every permutation, right? Even though it winds up duplicating some of the tests. Okay, so yeah, so you might see something like this. It might give you a headache, but it'll at least give you a look at which variables look like they're worth evaluating. So okay, so I'm going to go up here and analyze, and I'm going to go to correlation bivariate. And first thing I'm going to do is I'm going to look for a association. I'm going to look for an association or correlation in statistical terms between the weight gain during pregnancy and the birth of the infant in ounces, birth weight of the infant in ounces. So what's my null hypothesis going to be here? If I put it into words, I say that there's no correlation between weight gain during pregnancy and the birth weight of the child. And my alternative would be there is a correlation or association between the weight gain during pregnancy and the birth weight of the child. But if I wanted to state it like a true statistician, I would say my null hypothesis is R, the correlation coefficient, Pearson's correlation coefficient, R is equal to 0 is my null hypothesis, no correlation, or my null hypothesis or my alternative hypothesis, R is not equal to 0, which means that there is some kind of correlation. Doesn't say whether it's strong or weak or anything like that, but there is one. So I'm going to say, okay, let's see what we wind up with. And we wind up with the correlation between these two values is 0.222. Okay, that's interesting. That's not as strong a correlation as we looked at before in the fake data that I had. However, it is a positive correlation, right? You don't see a negative sign there. So as the weight gain during pregnancy goes up, typically the birth weight of the child goes up as well. Now, is this just due to chance? Can I reject my null hypothesis here? That's a question. That's my question to you guys. Can I reject my null hypothesis, say that R is not equal to 0? Maybe just equal to 0.22, positive 0.22, but is it really equal to, is it really statistically significant? Can I reject the null hypothesis? So one of you guys tell me that. What do you think? Even though it's not a strong association, can I still reject it? Yeah, because the significance is less than 0.05. Maybe only a weak association, but that association statistically is real, right? It's not due to chance, as far as we're concerned. So now we're going to go to our analyze, regression, linear, and now I have to make a decision. Does the birth weight of the baby cause the mother to gain weight, or does the mother's weight gain cause the baby to be bigger? I think the reasonable association there is that the mother's weight gain contributes to the birth weight of the baby. Okay, and I'm going to go ahead and say okay, and now we'll get our additional tables. And you'll see that, let's see, significant doses is the same thing, 0.22. Notice that before it lost the negative sign there. So you got to keep in mind that that negative sign is there. If it's a positive, this is a positive association, right? We saw that in the graph, right? And we saw that in the Pearson correlation coefficient. right? So keep in mind, you may lose it there when they give you this new chart. It may just give you that number. Now, remember R squared? R squared now, 0.22 times 0.22 is 0.049. It's 5%. What does that tell you? 5% of the variability in the baby's birth weight is due to the amount of weight that the mother gained. Oh my goodness. That means 95% of the birth weight, the variability in the birth weight is due to other factors other than the amount of weight that the mother gained. And that makes sense because as I'm not an expert in this, but we get a lot of, obstetrical nurses and also, doctors and so on and so forth going through this course. And they've told me over the time that we've used this data set, they've told me that very frequently that, mother's weight gain, a lot of that's fluid. It's not really, like increasing the size of the baby, and a million other factors affect the amount of weight that a mother gains, right? Not all of that really winds up affecting the size of the baby, right? Although this is an important factor, right? The birth weight of the baby is a very important factor in terms of the health of the infant, right? So that's what this tells us. It tells us that yes, there's an association, but it's a weak association. And only 5%, it only predicts about 5% of the variability, so that there's many other factors that are more important than this out there in terms of that affect the birth weight of the baby. We might actually take a look at another one. So what if I want to put together my formula? Well, my formula is going to be y is going to be equal to the slope 0.361 times x plus 105. Right? So let me get a piece of paper. So for this, right, my y is equal to, I like just doing it, you can do it any way you want. 0.361 is the slope times x plus 105.7 is the y-intercept. So if I wanted to substitute the actual values, this is the weight of the baby at birth, and this is equal to 0.361 times weight gained by the mother plus 105.7. So if the mother gained 30 pounds, and I wanted to predict what the birth weight of the baby is going to be, I just say 0.361 times 30 plus 105 is what my prediction is. And I'm just going to make a number up here that looks like maybe 10. I'm going to say that says something like 115 ounces, right? If the birth weight of the baby is 120 ounces, the difference between these two, 5 ounces, is the residual. Okay, in other words, the error in that particular measurement. Okay, so that's the way I would use this data. Now I'm going to go back now, and I'm going to go. I'll just do one more. I'm going to go back here, and I am going to say analyze. Let's see, regression, linear, and I'm going to take another set. Birth weight of the infant. I'm going to leave that, but I'm going to look for a different value here. I'm going to look for the, let's see, completed weeks of gestation. And I'm going to click OK. Let's see what we wind up with there. Okay, what is our R value there? Our R value there is 0.583. Okay, 0.583. Okay, that means R squared is equal to that number times itself is 0.34. This means that 34% of the variability in the birth weight is due to the number of weeks of gestation. Makes sense. It's important that's why doctors try to, if they have women that they're afraid will deliver early, the birth weight of the baby is going to be smaller, and they're more concerned about that. They'll try and extend the pregnancy if they can. Right. So that is an interesting tool for us. So what's this formula going to look like? What is this relationship going to be like? Okay, so now I'm not even going to bother to write in a math formula. I'm just going to go straight ahead and say that the birth weight of the baby is equal to the slope, completed weeks of gestation is the slope, which is 4.8 times x times the weeks of gestation plus or minus 70.4. Okay, so that's my formula. Okay, so if the baby is 40 weeks, that's roughly 200 minus 70 is about 130 ounces, right? I would just substitute the number of weeks of gestation there, multiplied by 4.8, and then subtract 70, and that would give me my predicted value. Now, the real interesting thing here is 4.8 is the slope, right? What does that mean? That means that the change in y over the change in x is equal to 4.8. So in other words, if the line looks something like this, that means for every one value I go up in x, right? In other words, for every extra week that we have this pregnancy, how much does y increase? Y increases 4.8, right? If x increases 1, y increases 4.8. If x increases 2, y increases 9.6. What does that tell you? That tells you that if I have danger of premature birth, if I can avoid delivering this baby for one more week, I can say that there's a good shot I'm going to get 4.8 ounces. That baby's going to be 4.8 ounces bigger than it would be if we didn't have that extra week. So it gives you an opportunity to understand how one variable impacts your outcome variable, and let you make all sorts of important decisions, like how important it is that we extend this pregnancy, how important it is that we devote this number of dollars to this particular kind of training program, how important is it that we give this drug to diabetics, and so give this number of units of this drug, or maintain this level of vitamin D in these pregnant women, compared to the birth weight of their baby, and it gives you an idea of what the impact of your decisions are. That's why regression is so valuable. That's why it's so popular in so many studies that you're going to wind up reading. Okay, now somebody asked me about R squared. Typically R squared that's a correction value that's associated with the number of variables that you're using. So in this case, R squared and adjusted R squared, they're very similar. There's only one variable, one predictor variable that we're using. Let me just, as an experiment, go to Analyze, Regression, Linear, and I'm going to do a multiple regression. I'm going to put two values here: completed weeks of gestation, and I'm also going to put in, what other values do I have here? Got the age of the mother, completed weeks of gestation, age of the mother. What else do I have here? Weight gain. I'm going to put in weight gain during pregnancy, right? Even though we know that's not that big an issue. I'm going to click OK. Well, now I wind up with two slopes. I wound up with 4.6 and 0.289 for the other values. Now, this would be, just without writing it down, the formula for this would be the weight gained, the birth weight of baby is equal to 4.6 times the completed weeks of gestation plus 0.289 times the number of pounds that the mother gained plus or minus 69.7 minus 70, the y-intercept. So your formula now has an extra value in it. So what does that do you? If I go up to the R value, well, the R value now is 0.588, and the R squared value is 0.345. So this is higher, I think, than it was before. So it may not be a whole lot higher, but it's a little bit higher. Sometimes you get a nice boost out of extra variables and stuff like that. The R square value, one of the functions of the R square value is to adjust the R square value for multiple predicting variables. So for the most part, for our analysis of simple linear regression, you would stick with the R square value for the stuff we're doing. Okay? And when you take a more advanced course in statistics and you get and you do more than a glancing review of multiple logistic regression, then you guys get an opportunity to re-examine that. But basically, I think that's really the best way to look at it for now. Okay, so I think that should go a decent way towards at least getting you through the homework and hopefully helping you be a little bit more prepared for the exam. Okay, yes, because the significance is low. Is there once I married? Okay, and could I ask a question on the microphone? Sure. Who is that? Okay, let me just see.
Hi, Professor. This is
Oh,
Noriel.
you're unmuted. Go ahead, talk.
Yeah, I had to switch computer. So just with regards to the R value that you get on the regression versus the the test score that you get on the correlation when you do correlation, it's the same number. Is that correct?
It's exactly the same. All it's doing there when you do regression, it's just repeating the calculation for the Pearson's R value.
And as the R value, I guess, as the correlation gets stronger towards 1, that the R square also goes up. The variability is that
Exactly. It tells you that that this value has more of an impact on the on the dependent variable than if it was just a smaller number. Makes sense, right? Because then if the correlation is weak and there's not much, all the points are all scattered around and stuff like that, then you say to yourself, well, knowing the independent variable doesn't help me that much, so it's not as predictive, right? So that's why the R square value goes down along with the R value.
And Professor, last question with regards to so this is multiple regression. How many variables could
As
you
many as you want. There's no limit on the number of variables, but
Okay.
you need to be practical. In other words, it's hard. One of the problems with multiple regression, and you might have seen it here, I didn't get that big a boost here. And the reason for that, it might be that if you really think about it, let me see where I was here. If you really think about it, let's see, regression. If you really think about it, the weight gained during pregnancy and the completed weeks of gestation, they're related already to each other, right? I mean, they're really kind of already have a relationship. They're not really independent of each other as predictors of the birth weight of the baby. So you got to be careful of that because it adds a confounder to this whole thing. So it's really hard in multiple regression. It's really hard to come up with predictive variables that don't like, for instance, if you start with a single variable as a predictive variable, it's hard. One of the hardest things is come up with another variable which is not associated with that first predictive variable, which is not already kind of built into that first predictive variable, as this is, right? Weight gain during pregnancy is really probably directly associated with the weeks of gestation, right?
Right. So if you if for example, if you get if you do the correlation and between two variables and you get a low association, and then you do the regression and you get a higher, I mean, is that possible? That
Nope. No,
no.
what's going to happen is you're going to get the same R value.
Oh, okay, right.
If the R is low, you're going to get a lower R square. If the R is high, you're going to get a higher R square. Right? So they're directly related to one another. So in that case, now it is true that depending on how you interpret in multiple regression, even just reversing the order that you put in the variables could affect the R square value, for you, in a multiple regression. And also, like if you combine different variables, it might affect it as well.
Okay. I was just thinking about how to minimize the like what you said, the confounder. So I guess you just have to think of it logically.
Right. You have to think about, could there be another association that's already buried into these? In other words, am I just adding a new variable that really is already accounted for in this first variable I'm using, or the second variable I'm using? Is that is that already built into something? Like, for instance, if I were gonna, if the associated variable, one of the variables here, if I were to the independent variable, if I were to put in BMI in here, right? Well, if I were going to do a multiple regression, I wouldn't use as a second variable height or weight, because height or weight is already a component of BMI.
Right.
Right. That's an outrageous, gross version of confounding this with something that's already built into the first variable. But it's sneaky. There's a lot of things that like aren't quite as obvious. Like, for instance, this one's not quite as obvious, right? Completed weeks of gestation, weight gain during pregnancy, they really are associated with one another. And they're really not independent of one another. So there really is, we kind of are introducing a little bit of a bias in this whole thing.
Okay, thank you.
Okay, guys. I think that should go a long way towards helping you, especially if you hadn't taken the exam yet and you're struggling with the homework or something like that. That I hope will help out. I may be able to get on again for about an hour tomorrow night. I don't think it's finals week, so we're not going to be in class or anything like that. But we can spend, if you guys have, what I'll do is, if you have questions, post them to the discussions board. And I will either answer them live or come back on live at about 8 o'clock tomorrow night. Okay, guys? So hopefully, if this is the last chance we get to talk to each other, have a great holiday. Finish up all your work, get it done, so you don't have to worry about anything this weekend. You'll be all done. Your hands will be washed of statistics, and you'll be able to relax until the end of January again next semester, unless you're graduating. And if you are, congratulations. But in the meantime, have a great holiday if I don't get to talk to you guys again. Take care.